Modern AI can both see and hear. You can show it a video, let it listen to the sound, and ask it a question. But here is something we almost never stop to ask. Inside the model, how does the sound and the sight actually travel through the network to produce the answer? This paper opens up that black box and traces the path. This is the paper from the University of Surrey. The models it studies are called audio-visual language models. Glue a vision encoder and an audio encoder onto a language model, so a single network can watch, listen, and talk. The authors set out to draw the first clear map of how audio and visual information move through these models. The study looks at two ways these models receive the world. One is a single audio-visual video, where each video frame comes paired with its matching sound. The other is multiple separate items, several images and audio clips interleaved with text. The big question is the same in both cases. Which path does each modality take to reach the final prediction? Why does this matter? Interpretability researchers have already mapped how images flow through vision language models and how video flows through video LLMs. But when you add sound, the inside of the model was basically uncharted. In particular, no one had traced what audio actually does on its way to the answer. So how do you trace information you cannot see? The tool is called attention knockout. The idea is simple but powerful. You let the model run normally, then you surgically block one specific group of tokens from attending to another, and you watch how much the answer changes. If cutting that connection wrecks the prediction, information was flowing through it. We measure that change as a single number, the relative shift in the probability of the correct answer letter. A large negative value means the blocked pathway was carrying information critical to the prediction. A value near 0 means it was dispensable. To be fair, they only run this on questions the model already gets right, so every drop is a real loss. The main model under the microscope is Qwen 2.5 Omni at the 3 billion parameter scale, with larger models checked later. The main testbed is a V-speaker bench, a speaker-centric benchmark. Its questions are clever. The clue lives in one modality and the answer in the other, so the model genuinely has to cross between sound and sight. The natural first move is just to look at where the model pays attention. For most of the network, the final token stares at the language tokens, and attention to audio and video fades away. But then something strange happens. Attention to the video suddenly spikes at layer 31 and stays high to the very end. Here is that spike. For 30 layers, video attention is quiet. Then it jumps. If you trusted this picture, you would conclude that the model is finally reading the video at the deep layers, right before it answers. That conclusion turns out to be completely wrong. The spike is caused by a handful of special tokens called attention sinks. These visual tokens light up with enormous magnitude and fire the exact same hidden dimensions as the well-known language sink. They are a mechanical artifact of that huge activation, not a sign of real visual content being read. They simply soak up attention. To prove it, the authors masked out the video and audio at those late layers entirely. If real information were flowing there, accuracy should collapse. Instead, it stayed flat and even ticked up slightly from 42.2 to 42.5. Deep attention spike carries nothing. So the first lesson is a warning. In these models, where the attention points is not where the information flows. Bright spots at the deep layers are sinks, not signals. To find the real path, you have to intervene, not just observe. Now the knockouts. First, where do the two senses actually mix? The answer is the early to middle layers, never the deep ones. Attention across video frames matters for almost every task, because the model has to stitch the frames into a timeline. Direct audio or video mixing only kicks in when a task needs tight alignment between what is said and what is shown. One subtle detail: mixing within the audio stream barely matters, because the audio encoder has already blended the sound before it reaches the language model. Video gets no such head start, so it leans on cross-frame attention inside the model to build its sense of time. The two modalities are simply prepared differently. And here is the route to the answer. It is a single, clean, sequential pathway. The audio and video pour their content into the question, tokens at the middle layers. Then the question carries that combined content to the final token, where the answer is decided. There is no shortcut straight from the senses to the prediction. The question acts as an aggregation point, a meeting place, because it sits after the audio and video in the sequence. And the mix it collects depends on the task. Visual questions flow mostly through the video. Questions that need fine-grained listening draw from both senses at once. The model spends its attention where the task demands it. So for a single audio-visual video, the picture is tidy. Senses into the question, into the answer. One pathway, with the balance of senses set by what the question is asking. The real world is messier. Often you give the model several separate things at once. 4 candidate images, plus 1 reference sound, and a question asking which image matches. The authors test exactly this with the AVLLM benchmark. Does the same single pathway still hold? The answer is no. The tidy single path breaks into parallel streams. The candidates talk among themselves, then both the candidates and the question pour into the reference. The reference now plays the role the question played before, the late meeting point that feeds the final token. There is a second, separate stream running in parallel. The candidates also feed directly into the answer choice letters. At the middle layers, the correct letter quietly gathers evidence from the candidates. So the decision does not jump straight from the images, it flows through the option letters. And the final token does not just read the winner. It reads both the correct and the incorrect option letters, and they actively compete. Blocking the correct letter hurts the answer. Blocking the wrong letters actually helps it. The prediction is a tug-of-war between the choices, resolved at the very last token. So the shape of the flow is not fixed. Give the model one fused video, and it routes everything through one sequential path. Give it many separate items, and it splits into 2 parallel paths. The architecture adapts its wiring to the input. Now comes the payoff. If audio and video hand off their content at the middle layers, then past that point, the model is carrying dead weight. The original tokens have already said everything they were going to say. So what if you just threw them away? That is exactly what they do. Discard the video and audio after layer 26, and the leftover question text after layer 29. The result is almost eerie. Accuracy does not fall. On several tasks, it even improves a little, because dropping the sync tokens removes a distraction, and it generalizes across 3 different datasets. And because the model now processes a shorter sequence, it runs faster. The prefill stage gets cheaper with no accuracy cost. It is a free lunch, handed to you by understanding the information flow. This points to a whole new way to compress these models, from the inside, layer by layer. Why does a late meeting point keep emerging? The authors point to causal attention itself. Because each token can only look backward, tokens placed later in the sequence are naturally positioned to absorb everything that came before. The question and the reference win that role simply by sitting at the back of the line. This also settles a debate. Concurrent work claimed that audio and video are integrated in the deep layers. But this paper shows those deep layers are dominated by syncs. The real integration happened much earlier. It looked like deep understanding was largely attention being soaked up by sync tokens. The appendix is full of careful detail. They track exactly when the syncs are born. The language sync appears around layer 15. Vision syncs show up much later, at layer 31, the very layer where that misleading attention spike begins. Same mechanism, different birthdays. They also stress test the method. They sweep the size of the knockout window and settle on 7 layers, wide enough to catch a pathway, but narrow enough to pinpoint it. And every headline result is reproduced on the 7 billion models, and on a second model family, Video Salmon 2. The story holds across scales and architectures. The authors are honest about the edges of their work. Everything here lives in the multiple choice setting, where the answer is a single letter. Open-ended tasks like free-form captioning or dialogue might route information differently, and that is left for future work. So here is the whole journey in one breath. Attention can lie, so the authors used knockouts to trace the truth. Inside one video, the senses funnel through the question into the answer. Inside many items, the flow splits into parallel streams. And once a token has handed off its meaning, you can simply drop it for free speed. This is the first coherent map of how audio-visual models orchestrate sound and sight inside the network. And it turns understanding into a practical tool for building faster, clearer models. If you found this useful, go read the paper. Thanks for watching.